షేర్ ఎంటైర్ స్క్రీన్ కొట్టండి సార్.
షేర్ దగ్గర ఓపెన్ చేసిన తర్వాత గ్రూప్ ట్యాబ్
ఎంటైర్ స్క్రీన్ కొట్టండి సార్.
ఓకే కొట్టాను. దీని తర్వాత అండి
మీరు ఏమైతే షేర్ చేయాలనుకుంటున్నారో అది ఓపెన్ చేయండి. మా షేర్
చేశాను.
రాలేదు ఇక్కడ, మరి షేర్ కాలేదు.
షేర్ అవ్వలేదు సార్.
షేర్ ఇక్కడ నుంచి ఎలా అవుతుంది అని
పైన చూసారండి మైక్ పక్కనే మైక్ లింక్ మధ్యలో ఉంది చూడండి సార్, ఒకసారి యారో మార్క్ లాగా.
ఒక్క నిమిషం షేర్
స్క్రీన్ షేర్ చేయడం
కావట్లేదు సార్.
ల్యాప్టాప్ లో చేయాలి కదా, అది చేయడానికి వాళ్ళు డిసేబుల్ ఒకసారి చూస్తున్నారు.
సార్ ఇప్పుడు మీరు డాక్యుమెంట్ ఓపెన్ చేయండి సార్. షేర్ అయింది మీ స్క్రీన్. అదే పీపీటీ రాలేదు సార్ ఇంకా. ఇప్పుడు వచ్చిందండి. అది ఒకసారి మాస్టర్ ఒకసారి ఇంకొక స్క్రీన్ కనిపిస్తుంది చూడండి, అది క్లోజ్ చేసి రైట్. దీన్ని ప్రెజెంటేషన్ మోడ్ లో పెట్టండి సార్. ప్రెజెంటేషన్ మోడ్ ఉంటుంది చూడండి సార్. ఇక్కడ కింద కార్నర్ లో 4 యారోస్ ఉన్నాయి చూడండి. అంతే సార్, అదే అంతే సార్. అట్లాగేనండి.
వరప్రసాద్ గారు నమస్తే సార్. థ్యాంక్ యూ సార్.
నమస్తే మాస్టారు. వరప్రసాద్ గారు.
మా వాయిస్ ఇస్ క్లియర్?
వినిపిస్తుంది సార్.
థ్యాంక్ యూ వెరీ మచ్ అండి.
బాగా ఇబ్బంది పడుతున్నట్టుంటారు జర్నీతో అటు ఇటు తిరుగుతా.
లేదు సార్, కొద్దిగా అనుకోకుండా చిన్నది అంటే ఇప్పుడు లైవ్ లో ఉన్నాం కాబట్టి చెప్పలేదు, కానీ కొంచెం హెక్టిక్ అయిపోయింది నాకు ఈ
తర్వాత మాట్లాడదాం.
ఓకే ఓకే సార్.
ఒక 2 నిమిషాలు స్టార్ట్ అవుతుందండి.
ఓకే ఓకే సార్, నేను లైన్ లో ఉన్నాను.
ఓకే.
వరప్రసాద్ గారు నమస్తే సార్.
సార్ నమస్తే సార్, ఎలా ఉన్నారు?
ఫైన్ సార్. థ్యాంక్ యూ వెరీ మచ్ ఫర్ యాక్సెప్టింగ్ అవర్ ఇన్విటేషన్.
థ్యాంక్ యూ వెరీ మచ్ సార్. థ్యాంక్ యూ.
వీడియో కనపట్లేదు ఇక్కడ మరి.
Yes, sir. Yes, sir.
స్టార్ట్ చేయమా?
Sir, please start the program, sir. Sharp at 4 o'clock. Go ahead, sir.
Good evening, one and all. On the occasion of 104th birthday anniversary celebration of a great mathematician, Dr. Komarolu Chandrasekharan Garu, and the 70th birthday anniversary celebrations of our former head of the department, Dr. Nagala Prabhakar Rao Garu, the Department of Mathematics is organizing a one-week international faculty development program on innovative applications of mathematics, IAM 2024, in association with Institutions Innovation Council, ICC. On the first day, Dr. J. Bhaskar Babuji Garu, Professor, Department of Applied Sciences and Humanities, Anna University, MIT Campus, Chennai, has delivered a talk on graph techniques for cyber security. On the second day, that is yesterday, Dr. C. Pavan Kumar Garu, Faculty in Mathematics, Apex Max Excel Center, North Carolina, USA, delivered a talk on linear algebra tools and its applications. For the above 2 days, each session was engaged with approximately 700 participants. Thank you one and all for your good response and valuable support. I request our head of the department, Dr. K.V. Nacharli Garu, to address the participants.
Dear esteemed faculty members, welcome to the third day of our International Faculty Development Program. It is an honor to address such a dedicated group of passionate participants. Our journey over the past 2 days has been a collective endeavor to enhance our skills and to expand our knowledge. I want to express my appreciation to each and every one of you for your sincere participation. It is through only your presence that we have transformed this event into a good platform for professional growth and collaboration. Throughout this FDP program, you will get an idea on innovative methodologies and emerging trends in research and education. The wealth of experience in participating in any FDP definitely may combine with increasing enthusiasm to learn new things and exemplifying to explore the spirit of continuous improvement. Today, our resource person is Dr. KNVV Varaprasad Garu from Department of Mathematics, Guru Ghasidas Viswavidyalaya, a central university, Bilaspur. He did commendable research on function analysis under the able guidance of Professor GVR Babu Garu from Andhra University. On behalf of Maths Department, I am thankful to our today's resource person, Dr. KNVV Varaprasad Garu, to accept our invitation for giving his valuable lecture in our international FDP. Thank you, sir. Thank you very much. In the third day's program, I am sure that the knowledge which will be shared by our revered resource person, Dr. Varaprasad Garu, which enables us to resonate in our research practices in function analysis. Let us continue to strive for excellence in education. Thank you, one and all. Thank you, Karnakar sir. Thank you, sir.
Okay, sir. Thank you very much, sir, for your valuable message. Today is the third day of the 1 week International Faculty Development Program. Today's speaker is Dr. KNVV Varaprasad Garu, Assistant Professor, Department of Mathematics, Guru Ghasidas Viswavidyalaya, a Central University, Bilaspur. Now I request one of our staff organizers, Ms. K. Sunita, to present profound profile of Dr. KNV Varaprasad Garu.
Good evening all. Welcome you all to a 1 week International Faculty Development Program on Innovative Applications of Mathematics. I am honored to introduce today's resource person, Dr. Koti NVV Varaprasad sir. Dr. Koti NVV Varaprasad sir is an assistant professor working in the Department of Mathematics in Guru Ghasidas Viswavidyalaya, Bhopal, a central university in Bilaspur. He did his MSc in Mathematics from Bharatpulaha Viswavidyalaya, MPhil from University of Madras, Chennai, and PhD from Andhra University, Visakhapatnam. He has published 21 research papers in various reputed international journals. 2 students have obtained PhD and 2 are pursuing their PhD under the guidance of Dr. Varaprasad Garu. He completed his one project sponsored by UGC of worth 6 lakhs. He delivered invited talks in various national and international conferences. He is a life member in various mathematical societies. Presently, Dr. Varaprasad Garu is working in the area of nonlinear analysis, that is, fixed point theory and applications. Dr. Varaprasad sir is praised by one and all for his best way of teaching from the last 3 decades. His soft nature, motivational behavior, teaching abilities, research capabilities are additional strengths to him apart from his goodness and vast experience in the field of education and research.
Thank you, Sunita, for your nice introduction about Dr. KNVV Varaprasad Garu. Now I hand over the session to Dr. KNVV Varaprasad Garu. Sir, we start the lecture.
Okay, sir. Thank you very much, sir. First of all, thank you very much to the Department of Mathematics, sir.
Sir, please start the lesson, sir. Lecture, sir.
Okay. Now, actually,
Varaprasad, sir.
Sir, is this voice is clear?
Sir, your voice is audible. Sir, please carry on, sir. It is very clear, sir.
Okay, thank you. So today's lecture is iterative schemes. My research field is that nonlinear analysis. Particularly, last time also I gave a lecture in this 5 days program, and that is in the different mode. Now, actually, I turned in the approximations theory, especially in the one of the innovative research in the nonlinear analysis, that is the fixed point theory in the approximations point of view. In this point of view, recently, when the student is also submitted thesis also, so it was increased my credentials. 3 PhDs are completed under my guidance, and 42 publications. It is modified. I am not given the modified by CV of myself to the Department of Mathematics of Babatla College. Whatever it may be, today's I would like to give dear participants. I will try to give a completely one innovative type and also clear picture about the today's lecture. Generally, we know the metric-based definitions and such things also. My entire content related to the fixed points. First of all, I would like to start from definition of fixed point. I would like to give this entire information in layman persons, bottom two. So I would like to read it out. Fixed point definition. Suppose let X be a non-empty set and T be a self-map on X, be a self-map. The point X is said to be a fixed point of T if Tx is equal to X, and then X is called a fixed point. In my presentation, I would like to show Ft is called a collection of fixed points of T. This is a notation. Time to time we can understand that. That's why I mentioned here Ft. And I would like to give some known examples. Known examples. That is, suppose let X is equal to R, and mapping Tx is equal to X square. Easily we can identify that only 0 and 1. These two are fixed points. These two are fixed points of T. Only two fixed points are there in this mapping. And if you are taking a Tx is equal to 2x plus 1, so easily we can identify that minus 1 is a fixed point. Compared to the first example, second example. In fact, the first example, two fixed points are there. In second example, one fixed point is there. In third example, Tx is equal to x plus 1, there is no fixed points. And if you are taking a phone, that means that Tx is equal to x. So every point is a fixed point. So this is a different type of examples I provided for understanding purpose. That means sometimes if you are defining any map, sometimes that mapping have a fixed point, otherwise it's only one fixed point, otherwise more than one fixed point, otherwise infinitely many fixed points is possible, depend upon the relation between the mappings. So these are some graphs I'm mentioning here. So easily we can identify that about the previous examples graphs also. So I would like to skip it out, these two general principle maps. Now I would like to, before going to be define the contract to definitions, I would like to, this is my right to present this definition. Ellipsism and continuous. Ellipsism mapping. This is continuous. Ellipsism. So suppose let us take XD metric space and T be a self map on X. And then you can say that T is said to be ellipsism continuous mapping. Ellipsism mapping. If there is a L is positive such that D of Tx Ty less than or equal to L times of D of Xy for all Xy in X. I would like to redefine in the next slides also. Even then also I would like to mention it here also. In this talk actually I would like to give a review of what is going to happen in this area research in present continuous research scenario. And this is a very emerging field for continuation of in this research also. Those who have an interest and they can follow up as this also. And this is the ellipsism mapping. And we know that if T is equal to L is equal, suppose L is equal to 1, then T is called a non-expansive mapping. And if X is different from Y, if you mention T is said to be contractive, if you are writing that D of Tx Ty less than L times of D of Xy. Now this is the known values, the known things also. Now come to the point of the general contraction condition. General contraction condition. Of course, this contraction condition is very famous. especially in the Banach fixed point theorem. Before going to go for the theorem, primary and first good theorem, very famous theorem in the Banach, I would like to give a definition about the contraction mapping. Suppose let us take XDV metric space, not necessarily complete. It is a complete metric space. That is this is a typographical mistake is happened in this definition. Not necessary. This is the XCBA should be complete. X is a complete metric space and F is a self map on X to X is any function. Then if function is satisfying ellipsis condition with the constant K, and K should be is equal to 0 less than K less than 1. If you mention it here it is like this, then F is called a contraction mapping. Now, one of the famous theorem that is called Banach contraction principle. This is a very famous theorem. Let X be a complete. I would like to read it out. This Banach contraction principle. Let X be a complete metric space, and T be a self map. X to X is said to be a contraction mapping, and with the ellipsis constant alpha. Here it is alpha I mentioned here. Then T has a unique fixed point. This is the most famous theorem in 1922. This is Banach says proved this theorem, and of course we know the way of proof of this thing is also. I would like to mention it for understanding purpose is like this is step 1, step 2, step 3. We are going to be defined. This is the xn plus one sequence part, and second that we have to show that whether it is a decreasing sequence, Cauchy sequence or not. After that, we are going to be show that whether the initial point is a fixed point or not, and also finally we are going to prove that whether it is uniqueness or not. This is also those who studied in metric space or function analysis. They already knows that the Banach fixed point theorem proof also. That's why I'm not mentioned to how to prove this one. I'm giving a stepwise like this also. Generally, after Banach theorem, there is some questions are arised, and also before going to be discussed about the questions, and this after that many mathematicians have generalized Banach contraction principle rule in a different ways. One is the way is they are changing the space and weaken the spaces also. And Banach fixed point theorem is under complete in the setting of complete metric space. It was proved already. And one way is the space is relaxed. Second way is the contraction conditions also relaxed, and also it is developed and generalized also several type of. And also third is that using the construction of a sequence xn plus 1 is equal to t4 and x naught. This is actually generally called, this is the successive approximation Picard iteration. This is, and there is another type of research is developed change of the construction sequences. I would like to in this talk I would like to give some information and useful information, especially in this point of view, iteration construction sequence point of view. I would like to discuss in this talk. Generally, in the space setting, they are in the space setting. Several fixed points are developed, and we get the complete metric space, metric space, B metric space, and relaxes them. Next, cone metric space, and recently relational metric space. A partially ordered metric space, SB metric space, S metric space, D metric space, and extra. So many mathematicians are changed the relaxed the space is going to be changed, and they proved in the developed and very good theorems, not only for the Banach and generalized also. So space was generalized. In that point of view, many mathematics research papers are fixed point theorem papers are published in reputed journals also. Another point is that one of the most important, before going to be taking my talk, I would like to give a one good information regarding of the contraction principle. After that, I will go for my iterations process. Actually, Banach contraction principle use the condition is the contraction condition. By default, this is the D is a contraction condition. It should be a continuous. It forced to be continuous. It should be T is a forced to be continuous. If you are taking in any example, whether it is a that example have a fixed point or not, we have to verify the three conditions. One is that whether it is using the domain is a complete metric space or not. Second, whether the given mapping is satisfying the contraction condition or not. Once these two happens, we can conclude that definitely that taken mapping is have a unique fixed point. And it should be continuous also because contraction condition should be continuous. It is also proved in the BEC level textbooks also. They mentioned in the questions in the exercise questions also. And now question is arised in one of the great mathematician. Is it possible? Is it possible? Is this any possible to create a theorem which is a discontinuous mappings? If it is a discontinuous mappings is existed, how we can say that whether it is has a fixed point or not? So this is a very great open question at that time. After that, our Indian mathematicians, that is a Kannan, Professor Kannan sir is give a very affirmative answer about that thing. That thing. Also, he gives one example. Gives one theorem also. He used one contraction condition, and just like of this is, I would like to show. I'm going back one slide. D of fxfy less than equal to k times d of xy is a contraction condition. But Professor Kannan sir is used one condition d of fxfy less than or equal to k times d of xtx plus d of yty. K times d of xtx plus k d of yty. And k should be lies between 0 to half 1 by 2. If he used and proved theorem and also he got it a good result also, that means any discontinuous mapping, definitely we can say that that is discontinuous mapping is also have a unique fixed point if it is satisfying the Kannan's condition. So Kannan condition, if it is satisfied like this also, I think so it is also there in my presentation. I would like to check it now. One more example is also given here. A good example that 0 to 1 by 2. Before going to be Kannan contraction, I would like to view these good examples also. 0 to semi-integral 0 to 1 by 2. Equipped with the metric on absolute value. This is clear that is in incomplete metric space, non-complete metric space. And it is d of xtx is self-map, dx equal to x square is a contraction, that is no fixed points. So in this example says that complete metric space domain is also very necessary. If complete metric space is not taken, then we cannot say T has a fixed point or not. When a fixed point principle, he says that space should be a complete metric space and T is a contraction, then only we can self-map and then only it has a fixed point. In this example says that space is not complete. Once space is not complete, we cannot apply the Banach condition. We cannot give the fixed point. No fixed point. This is an example which is not satisfying which is not fulfill the Banach contraction principle. Second example, condition. Condition is also very necessary. If condition space is continuous, and if condition is not contraction, then only we cannot say that it has a fixed point. These two are very good examples also. And one applications. Banach and very especially Banach applications also very useful also with using of the integral equations. They have a one condition. One example is also it is also there in any metric space condition. I would like to interest to discontinuous mappings. Oh, now it is I'm going to be discontinuous mappings. Already I told, once again, I would like to read it out and very fastly, I would like to go for my presentation area. Before going to be enter my presentation area, see this one, Kannan is in 1968, he solved the BA roads, open question, have any discontinuous mapping is the just that. So this is a 1968 is published in Kannan's operator. This is called XDB is a complete metric space, TB is self maps and X2X is a mapping. There is just a is lies between semi-interval 0 to 1 by 2, and this condition is that condition number is I am giving d of tx ty less than equal to a times d of x tx plus d of y ty for all x, y, and x, and then it is called a t is a Picard operator. Picard operator means that this t has a fixed point, and this condition is called a Kannan contraction. So Kannan contraction, this t need not be a continuous. If any mapping is satisfying the condition 3, what is presenting in the presentation, what is condition 3 is satisfies. Definitely, if it is a complete metric space and A should be the license 0 to 1, definitely that mapping is have a unique fixed point. And also, and t need not be a continuous. Same pattern Chatterjee is also proved. Same pattern Chatterjee also proved. Chatterjee also proved that condition is just, I would like to, before going to be slow, mention this slide. Chatterjee is also proved. So see this one, just he replaced x is equal to and y equal to x. That means d of xty plus d of ytx. If it is replaced, that is called a Chatterjee's mapping also. Same condition, rest of the parts are same conditions. So that theorem is also proved for a discontinuous mappings. What is the discontinuous mappings? See, is this possible? I would like to present one important theorem. I would like to give two important examples. See this one. Before going to be enter the one of the newly developing research area, and also say first example. What is the first example? These are examples only. We are not given this example for the Kannan contraction or Chatterjee contraction. See this one. Let x is equal to r. Let x is equal to r. That r is a complete matrix, of course. Tx is a self map, and every finite set is also this one. Tx is equal to mapping is defined 0. X is lies between 0 to 1, and x is equal to 1. Result is a 1 by 2. See this one. What happens? This is that this is the definitely this is a discontinuous mapping at 1, and fixed point is 0. That means particularly one we have to observe that the mapping is continuous at fixed point. Fixed point is a 0, not 1 by 2. Fixed point is a 0, but at 0 it is a continuous. Totally the mapping T is a discontinuous. Where it is a discontinuous, 1 is a discontinuous and has a 0. And the second example gives that. I would like to give a second, I would like to show the second example. Same as x is equal to r and t is the self map in x to x. Tx is equal to 1 by 2 and the semi-interval 0 to 1 by 2 and 1 by 3, 1 by 2 to 1. So that means here if you are observing that it is a discontinuous. Where it is a discontinuous? 1 by 2 is a discontinuous. If 1 by 2 at a discontinuous and 1 by 2 is a 1 by 2 is also a fixed point. Therefore, in this point of view, two research areas. First point is that no need whether it is a T is a discontinuous, that is sufficient. Whether it is a discontinuous or not. Discontinuous point is not important. Second point is that discontinuity is also definitely at fixed point. Second, due to second point, present running research area also. So present running area. So they are proving some results also. Particularly if the conditions is also conditions also definitely at fixed point it should be continuous, not more than that, not other than that point. Second point is also research is going on, but I am not concentrated about the second topic. That will be in the second different area. discontinuous at a fixed points. That is called discontinuous. I would like to give just for example purpose especially in this talk only. My presentation area is also different. Now already I mentioned it Chatterjee. I mentioned it Chatterjee condition. That is also already I mentioned. Read it out just 2-3 minutes before. This is the Chatterjee's theorem also. T of Tx dy less than equal to b times of x dy plus d times of d of y Tx. This is also because this is called the Chatterjee's mapping. So that is after Banach's fixed point theorem. First Kannan, after the Chatterjee is also proved two fixed point theorems for discontinuous mappings. But they are not mentioned. It is a hold for whether it should be discontinuous for discontinuous mapping only, not at a fixed point, not at fixed point. Hoga nahi hoga. That means ho sakta bhi hai. Next, now after the 1972, the one of the great mathematician is also proved very great theorem. Due to this great theorem, I would like to mention it this importance about also. That is what is that? There is a 1972 Zamfir school generalized Banach, Kannan, and Chatterjee also. So what is this theorem statement? I would like to read it out. This is let XD be a complete metric space and T be a self map on X to X be a mapping for which there is just a real numbers alpha, beta, gamma. Alpha lies between semi-interval 0 to 1 and beta and gamma lies between 0 to 1 by 2. And also at least one of the following is true. Definitely it should be called a it has a unique fixed point. Looks like there is no importance, there is no innovative in the Zamfir school. Looks like, but it is a very great idea about at least any one of the following is true. That means sometimes if mapping is continuous and also sometimes some area continuous mapping, some area is satisfying the Banach contraction, some area is not satisfying the Banach contraction. So that time that area is satisfying the Z2, then sometimes it is Z3 also. Any one of the condition, if it is a horse like this, definitely it has a unique fixed point. It is a very great theorem and also important theorem. For this important theorem, we are going to be enter the my field. I mean present talking field also. This is the Zamfir school's theorem also. This is some iterations. Now come to the my area. I mean present topic area, not my area. Presentation topic. Some fixed point iteration procedures. What is the some iterations? What is the some fixed point theorem procedures? I would like to. So it may change the slides. Okay, first of all, I would like to give a brief definitions. After that, I will go for the depth also. This is the equation number 5. That is xn. Xn means xn is equal to txn minus 1. Otherwise, we can write it to t4 and x naught. And this is called a Banach successive approximation method. Otherwise, it is called Banach contraction. Sorry, Picard contraction. After that, there is a Krasnov-Selinsky iteration. What is the Krasnov-Selinsky iteration? That is the xn plus 1 minus lambda times into xn plus lambda txn. It is we can say that this is called Krasnov-Selinsky iteration. It is Krasnov-Selinsky iteration. This is, and if you are taking lambda is equal to 1 in 6. Lambda is equal to 1 if I'm going to be take it at 6 equation, if I'm taking a lambda is equal to 1, definitely xn plus 1 is equal to txn. That means Krasnov-Selinsky iteration reduced to the Picard iteration. So after that, in place of lambda, 1 is taken the 1 sequence. I would like to mention it. This is a Shikawa. This is one iteration. See this one. This is the one iteration. Suppose let X be a I mentioned it real normal space. and T is the self map on X, E to E, that is, and the self map X naught is an arbitrary point. The sequence Xn is given by Xn plus 1 is equal to 1 minus alpha n, and Xn into plus alpha n times of Txn. And this is n is equal to running from 0, 1, 2, 3 up to so on. Here it is, what is alpha n? Alpha n is in a sequence which is lies between the interval 0 to 1, satisfying the appropriate conditions. Depend upon the theorems we are going to be mentioned it. It looks like it is a convex structure. So therefore, the xn plus 1 is equal to 1 minus alpha n xn plus alpha n txn. Therefore, here it is, if alpha n is a constant, if you are taking any constant, a fixed sequence is a fixed. If your sequence is a fixed, definitely it should be reduced to the Krasnostarsky iteration. If you are taking an is equal to 1, if you are taking an is a constant sequence, an is equal to 1, definitely it is reduced to the Picard iteration. So therefore, Picard iteration scheme is a case of one of the cases of the maliterations. This is the one of the important also, and also one important examples also. If you are for all participants, I would like to give a one thing is also Tx is equal to 1 minus x. See, please listen carefully. Tx is equal to 1 minus x. Domain is a 0 to 1. Domain is a 0 to 1. Tx is equal to 1 minus x. What is the fixed point? X is equal to 1 by 2 is a fixed point. Mapping is that Tx is equal to 1 minus x. Lies between a domain is a 0 to 1. Definitely x is equal to 1 by 2. But what happens if you are applying the Picard iteration scheme? Definitely we will not get the answer. And your constructed sequence by Picard iteration, it cannot be reduced to the equation. Suppose let us take it x is equal to 1 by 3. 1 minus 1 by 3 equal to 1 minus 1 by 3 equal to 2 by 3. 1 minus 1 by 3 equal to 2 by 3. Again 1 minus 2 by 3 is equal to 1 by 3. So therefore sequence is cannot be 1 by 3, 2 by 3, 1 by 3, 2 by 3, 1 by 3, 2 by 3, something like that only. Definitely by using Picard iteration, by using a Picard iteration scheme, your sequence cannot be convergent. Therefore, Picard iteration scheme is a fails for particularly some type of examples. Therefore, there is another type of iteration scheme is essential. For this purpose, MUN is introduced there one iteration scheme, just like what I mentioned in the equation 8. That is xn plus 1 is equal to 1 minus alpha n xn plus a alpha n into txn. Of course, I mentioned it an, but generally we are using alpha n also. Therefore, what happens? This is therefore MUN iteration scheme. What I mentioned previously with tx is equal to 1 minus x, that sequence definitely convergent by using MUN iteration scheme. That means some examples also adjusted which is not useful Picard iteration, that in that area MUN iteration is also useful. Sorry for the inconvenience to you. Therefore, this is the MUN iteration. After that, there is a developed one iteration scheme also. One iteration scheme that is the very most important iteration scheme. This is the let X be a convex compact subset of a Hilbert space. Of course, I take it the space is the Hilbert space, not necessary. We are taking a Banach space also. And T is a self map on X to X. But T is a self map on X to X, and pseudo contractive, using the pseudo contractive, that is not necessary. But here it is the Ishikawa iteration scheme only you can observe that is the 9 is a iteration scheme, that is Yn is equal to 1 minus Bn xn plus Bn txn xn plus 1 is equal to 1 minus an xn plus an t by n. This type of iteration scheme is called Ishikawa iteration. And an and bn, they are two sequences. These two sequences are lines between 0 to 1. There is no relations between alpha and whatever the alpha and whatever the beta. An and bn. But depend upon the theorem to theorem, we are going to pose some relations between A and B, whatever that may be. For conclusionally, we can say that the showing of mean equality 9 is called a Ishikawa iteration scheme. That means that definitely we can say that two-step monetization schemes. Two steps monetization schemes we are going to be mentioned it. Here it is in the next slide, I think. So maybe we are giving some relationship between the such things also. See this one in the Krasnov-Selinsky iteration. In the Krasnov-Selinsky iteration, lambda 1 is equal to 1. If you are taking, definitely Krasnov-Selinsky iteration is reduced to the Picard iteration. In the Munn iteration scheme, if you are taking alpha n is equal to constant, definitely Munn iteration scheme is reduced to the Krasnov-Selinsky. And if you put Bn equal to 0, Ishikawa iteration reduced to the Munn iteration scheme. That means that two Munn type iteration scheme is called Ishikawa iteration is more than general the Picard and Ishikawa and such things also. So therefore, after that also several mathematicians is also introduced different type of iteration schemes, and they proved very good results also. What is the necessary about the iteration schemes? Number one, so convergent, what is the necessary? In this point of view, Vasily Birinde is also recently he developed very good theorem also, Banach contractions, generalize the Banach contraction condition, and he posed the one, and he's also given one important definition also. I'm going to be mentioned shortly within a couple of minutes. I would like to present in my talk also. At the time, I will explain what is the useful also. So this is this one, and now come to the point in the contract to conditions. It is what is going to be happen here. It is now it is fixed point theorem on Jam-Firesco operator by monetization process. Generally, what happens in the after developing the Jam-Firesco theorem, he used complete metric space, and he used Picard iteration scheme, and he used respect to condition, Jam-Firesco condition, Z1, Z2, Z3 condition, and he proved it. Definitely, it has a fixed point also. Now, question is that can we change the iteration scheme? So he used the Picard iteration and he proved it also. Definitely, it has a fixed point if they are using a Picard iteration. So Munn iteration scheme is a more than it is generalized of the Picard iteration. That means the Picard iteration scheme is also subcase in Munn iteration scheme. Now, the question is that, so what happens? It is, and also it is proved. It is also proved. So, if you are taking the Banach space condition, before Banach space condition, convex structure, closed convex Hilbert space, closed convex Banach space used also, they proved also. But the generalized theorem I am taking here, what is the, let E be a Banach space and K is a closed convex subset of E, and T is a self map on K, and Jam-Firesco mapping. Jam-Firesco mapping means that at least one of the contract to condition, either Banach or Chatterjee or Kernan condition. Then iteration scheme is changed. That is xn plus 1 is equal to 1 minus alpha and xn plus alpha and txn. They are not using the Picard iteration. They are using the Banach contraction. They are using the iteration scheme only. And with alpine, and they have posed some conditions. What is the alpine? Alpine is the lies between 0 to 1 is the compulsory, and alpine should be Davatas. If you taking the if we posing these conditions, definitely this Jam-Firesco conditions also converges to the unique fixed point of T, and proved it also. So that means Jam-Firesco theorem, and also we can use either Picard iteration scheme, otherwise otherwise malnutrition scheme also. And also there is a question whether it is approved or not in the Ishikawa iteration also. Same question, whether it is the same question, whether it is approved or not. It is also approved. It is also approved. And also penetration, let E be a arbitrary Banach space and K a closed convex subset of E, and T be a self maps on K, and the Jamfins mapping, and alpha and beta is the two mappings and satisfying the following conditions. What is the conditions? Alpha n means alpha and beta n should be lies between 0 to 1. Alpha n should be diverges. And if you are taking any initial value x naught is in k, then iteration scheme, Ishikawa iteration scheme is also converges strongly to the unique fixed point of t. So this is the one example. This is the one example in literature for learning purpose. Those who are going to be doing the research, especially in these iteration schemes, this is we can if anybody studies of these theorems, they can understand that what is going to be happened also. After that, basically Bind is also and also proved it. Which one is good? Which method? Three methods are there: Picard, Mann, and Ishikawa iteration. Which method is good for this mapping? That is also we are going to be discussed in the incoming soon minutes. And I would like to this is the I would like to close this sharing, and now please hold on. Okay, thank you. Very good. Is it okay? Is it okay? Okay. Okay. Now I would like actually that is thing is actually I shortened the 20 minutes talk I gave in my department for encouraging of those who are belonging to fixed point theory, the initial stage. Maybe it may be useful to the those who are interested in the that thing also. Now I would like to give in this talk the review point of view only, not for the particularly big contents. I would like to use this platform. What is the importance is also. I would like to give a brief introduction. Now we actually, the first 3 lines is already mentioned in the previous slide. Now we'd like to take the review of on fixed point iteration procedures. I prepared the one notes of a student point of view, some booklet, I think so maybe 95 pages. In that point, maybe it may be useful. Failed to convert these presentation in the PPT. Therefore, I would like to use this content is like, as usual like this. So see this one PDF. This is the equation already I mentioned it. Xn plus 1 is equal to Txn, and that is called a successive approximation, or we can say the Picard iteration scheme also. And the next equation is called a contraction mapping. And we know already K is equal to 1. It is mentioned already. And see this one, 1922, Banach considered contraction maps and established the existence and uniqueness of a fixed point contraction maps by using the technique of convergence of a Picard iteration scheme and a complete matrix expression. The limit of the Picard iteration to the iterations is the fixed point of the contraction maps. Now, this is the Banach contraction rule. I mean, fixed point theorem, a complete structure point of view only. Generally, it is mentioned. This theorem statement is like this also. This theorem statement is also mentioned in the rate of convergence also. So we are going to be discuss about only iteration scheme. Therefore, I am not touching the present. Later on, within a couple of minutes, we are discussing about that thing also. So Xn plus 1 is equal to Txn is we are using generally in Picard iteration scheme. So come to the point here. Already I mentioned it. So Birinde, what Birinde happens? Birinde is a very famous mathematician, especially in this area. And also he proved a very open question also. Picard iteration scheme is the very best compared to the MUL. So now come to the point what he says that, and also it is easily understand. Few minutes back I also mentioned this example, and once again I would like to show this example on the screen also. See this one example 1.1.2. 1.1.2 tx is equal to 1 minus x. If you are taking 1 by 2 is a fixed point, it is easily identified that. But if you are taking any initial value which is lies between the domain, definitely you cannot reach that sequence to the 1 by 2. If you are taking 1 by 3, that means 2 by 3, 2 by 3, 1 by 3. It will be shifted. If you change any point, except 1 by 2, if you are taking, that's why we cannot reach it. That means definitely Belinda is observed that also. And this, especially this example, is not, Picard iteration scheme is not worked on it. Picard iteration scheme fails, does not converge to R. Therefore, then money iteration comes in the field, and he views that thing also. And also I mentioned it 1.1.2.1, that is the iteration scheme also, 1 minus alpha n and xn plus alpha n txn. This is already mentioned, and sigma alpha n is useful that also. And also it is mentioned it Krasnoselski, already we discussed in the few minutes back also. And see this one here also, one of the great example, very good example. Here if you are observing that one example I mentioned here as an example 1.1.3, it is not me, it is the great mathematician late Professor B.E. Rhodes, Billy Rhodes. He died recently in the corona time. So he's, what is the mention here? He is a continuous map. He is a continuous map, and for any x naught in k, the monetization scheme, the monetization procedure is convergent to the convergent point P. So that means always monetization iteration scheme, if you are applying, it does not converge always to the fixed point. It may be convergent to the point only. That may be fixed point or not, that will be different. One example is I mentioned 1.1.3 is mentioned it here. If you are observing this one, take the self map and close interval 0 to 1 to 1, and at 0, at x is equal to 0 and 1, result is a 0, and the rest of the part, that means 0 to 1, it is a 1. Definitely it is D is not a continuous. And FT means that a collection of fixed points at 0 is a singleton set, that is 0. And the fixed point set of fixed points is 0. If I choose alpha n is equal to 1 by n plus 1, definitely it is not converges to 0. It is converges to 1. Therefore, monetization scheme is converges to 1 only, not at a fixed point. That is also drawback. Depend upon the spaces on conditions only we are going to be such things also. For this purpose, they are very most variational discussion is also there in the Datson's book also, and B.E. Rhodes' book also, and basically within the iterative approximations, and Springer's recently published a book, and that thing also we basically is also discussed in this point of view. And previous slide I mentioned it. This is what happens. This is okay. It's okay. Oh, it is a Picard iteration. Belinda is confirmed. Now 19074 already it is mentioned in the previous slides also. Once again I mentioned it here. So running way, I would like to read it out within 15 seconds. 1 minus 2 steps of iterations, xn plus 1 is equal to 1 minus alpha n into xn plus alpha n t yn, and yn is equal to 1 minus beta n xn plus beta n txn. Alpha n beta n should be lies between 0 to 1. I'm reading fast. Don't be thinking I'm fast, because I would like to show these two iterations. Next generalized iterations is also coming in the next pages also. We have to observe what is the generalized concepts also. At the same time, if I found the typographic mistakes, I mention it immediately. Now, before going to be go for the next iterations. These are I'm mentioning only what type of iterations in literature is adjusted. Depend upon the mapping T. Actually, I gave only four contraction conditions only. Not only these four are fixed. Several contraction conditions also you can apply. What is we are applying? Picard, Banach contraction we can apply, and it is also over for these information only for the learning purpose. And also Banach contraction next Kannan contraction used, and Chatterjee contraction is also used, and also that Jamfilsky contraction condition also used. After that also several contraction conditions, strongly pseudo contraction condition, accretive contract condition, hemi contractive condition, lambda contractive condition, such contraction conditions also used. But I'm not to give in that area. Just I'm discussing about in the present in the literature, that is this iteration schemes I'm giving. What is present is available in the literature I'm giving. Later on we go for the such things also. One some students is raised hand. So sorry, can I give chance to the fellow? Otherwise, after finishing the talk, we can ask. Okay, so my dear participants, I would like to request you to all participants, note down your questionnaire. After completion of my presentation, I will give a time to you. You can ask questions after completion of my presentations. Therefore, hence I request you to no need to raise your hand. Once complete, then I will give an open question area. At that time, you may pose your question also and try to give your answer.
Sir, excuse me, sir.
Sir.
Dear participants, whenever you have any doubts, we have a question and answer session at the end of the session. We'll give sufficient time for you. Sir will clarify your doubts. Be patient. Sir will clarify doubts at the end of the session. So please wait. After completion of the class or nothing but this seminar, you can ask your doubts. Sir, thank you, sir. You can start, sir.
Thank you very much. Dear participant, please note it out. If you have any doubts, you can definitely give it. So after that, there is some collection of presentations. Collection of some iteration schemes.
Sir, you can start, sir.
Okay, sir. Is it readable now? Audible now? Is it audible? Sir, is it audible?
Sir, is it audible, sir?
Okay. Thank you very much. Sir, and now we would like to go for some schemes, iterations, procedures schemes also I'm going to be mentioned what we are going to be mentioned. Some examples I mentioned in the presentation slide in the slides. That means SP iteration procedure, CR iteration procedure, Picard S iteration procedure, and APAS procedure, and Nazir procedure, and node procedure also. After that, there is after Ishikawa iteration, one famous mathematicians all introduced the new iteration procedure also. Now, what is the new iteration procedure? Means that is a three-step iteration procedure. Three-step iteration procedure means that like this. This is the xn plus 1 minus alpha n plus xn plus alpha n tyn, and yn is equal to 1 minus beta n, xn plus beta n txn, and zn is equal to 1 minus gamma n, xn plus gamma n into 1 minus 1 into xn. And there is one question is definitely one question is possible. Then we can introduce the four-step iteration. What is going to be happening? So what is going to be happen sometimes? And so if after three-step iterations, if you are applying the four-step iteration also, we can get the convergence also. But it is reducing the convergence is also very negligible. So at the time of examples, we are also finding that four-step iterations also not, and I think so we can negligible things also. That's why up to Noor only we are considering. There is no, we are not considering more than that also, because sometimes what happens in some examples also Taylor's theorem, such things, if you are applying the numerical values after certain area, we are going to be neglecting the rest of the part. Just like of also this iteration schemes also, we are not using the more than the 3 iteration schemes also. After that, several iteration schemes also developed in this generalized also. What is generalized these things also? See this one in 2007. Agarwal and Oregon, Agarwal RP, Ravi P. Agarwal sir, Professor Ravi P. Agarwal sir and Professor Oregon sir and D.R. Sahu, Banners in the University Professor, Senior Professor Banners in the University D.R. Sahu sir is also introduced a new iteration scheme. It is also very famous. New iteration scheme, namely that is called S iteration procedure, which is an independent of both the Mann and Ishikawa iteration procedures and studied the convergence of contraction mappings. This is the independent. That means of no relations between Mann and Ishikawa. What is happens? It looks like it is the same. That means the structure is going to be defined. It is xn plus 1 is equal to 1 minus alpha into txn. And the post t is here. That is the t is 1.1.3.3. Then that post it is a t here. That is the txn plus alpha and tyn. And yn is equal to 1 minus beta n and xn plus beta n and txn. Especially in the t, in place of t, it is t. Definitely, it should be man. Or if you are taking in that area, if your t is absent, then it will be reduced to Mann iteration scheme also. And now, then alpha and beta and sequences are 0 to 1, satisfying the conditions of alpha and sigma alpha and beta and 1 minus beta and is divergent. That means this condition, especially this condition, at the time of the proof, this is needed. Theorem to theorem, condition to condition, this we can pose depend upon the scenario. We can write it. This is which is needed. We can observe the Taylor theorem. And Sahu is also taken. Sahu is Professor Sahu is taken. This is the sigma alpha and beta into 1 minus beta is equal to infinity part. This is after that there is a one iteration scheme is also. This is the same thing. I think so. It is 1.1.3.4 is also some mistake is there. Then 2012. In 2012, Renu Chao and Kumar is introduced the CR iteration procedure. In the CR iteration procedure, the 1 minus the beta n, and this is also 3-step iteration procedure. And if you are observing this one, only yn area, they are applying a t only. So one question definitely it is arises. What is going to be happened in the different different type of iteration schemes? That means sometimes it is there, sometimes it is absent. If what is the result is going to be importance about this thing. But definitely these results, these schemes are very important. If you are observing the numerical area, numerical examples and the numerical area. Once if you are applying definitely 1.3.5 inequality, if you are applying in place of especially yn area, if you are taking yn is equal to 1 minus alpha and txn, that means of t is equal to, if you are not taken, that is just like of that is the Mann iteration, is a new iteration scheme also. But convergent area, initial convergent speed of convergence is also comes very fast if you are applying 1.1.3.5 comparing to the new iterations. In that paper, Renu Chau and Kumar paper, they are also given the importance of this iteration scheme also. Once we are applying this iteration scheme, then we can understand that what is the importance of this one. And this is they mentioned it here also. This is S iteration procedure is a special case of CR iteration procedure. Of course, it is easy to observe that. It is easy to observe that. What is mentioned here? Gamma n is equal to 0. Gamma n equal to 0, then it automatically it is reduced to this one. And this is Gaurasa and Karakaya. This is very famous now. And the 2014, recently, 1 decade before, it is published. It is in this step 1.1.3.6 is also iteration scheme. 1 step Picard, 2-step Mann iteration procedure. one-step iteration of Picard and two-step monetization procedure. Recently, in 2024, one paper is also published. In that paper, also they mentioned it also, but unfortunately, I'm not entered in this talk. One paper is also mentioned. What is important? So, in see this one 1.1.3.6, one-step Picard iteration, two-step monetization procedure. So he introduced 2014 is this one. Professor Abbas and Nazir, they very good mathematician, good combination mathematicians. They introduced here three-step iteration procedure, but they applied in the xn plus 1 is equal to 1 minus alpha and t by n. So this time they are applying it two times also. Xn plus 1 is equal to 1 minus alpha and t by n plus alpha and t zn. And yn is equal to 1 minus beta and txn plus beta n t zn, and zn is equal to 1 minus gamma n xn plus gamma n into txn. Alpha and beta and gamma n, these are lies between 0 to 1. And Karakaya, now it is a new thing. Now it looks like it is easy, it looks like, but we cannot, we can post this iteration procedure easily, and we have to prove that whether it is possible or not. Convergence, you are getting a convergence or not, applying the respective contractive conditions. What type of contract can depend upon the contraction conditions also, it has to take it the additional information also. See this one, Karakaya and all introduced two-step iteration procedure, and their entire converse structure they are applying a T. See this one, especially this type of is also contraction that recently it is also DS officer also worked on this area also. Xn plus 1 is equal to T of 1 minus alpha and yn plus alpha and t by n. And yn, T of 1 minus beta n xn plus beta and txn. That means you have to take it the element from the converse structure. This is T of 1.1.3.8 alpha and beta are sequences in 0 to 1 also. And this is in 2016, Ulhan Darshad. Ulhan Darshad is also the same procedure, but he applied it as a xn plus 1 is equal to t by n. That means one step Picard and two steps Karakaya's conditions. This is also one of the conditions, and you can observe that with using of using of these things we can work on it also. And now we are going to be discuss about the comparison of the rate of convergence of fixed point procedures. Now, this is the very most important thing area, especially in this area. In 1976, one important point is mentioned in his paper, B. Rhodes. 1976, B. Rhodes, he compared two iteration procedures. And compared it. This is a comparison is also very important. Two iteration schemes, when it's Man and Ishikawa, Man and Picard, Man and Noor, Ishika and Noor, whatever the procedures we are taking, they are comparing what is the relations, which one is good, which one is a good. For that purpose, they are giving us some important note. Note means some important information. What is that important information I mentioned here? This is the this one is that terminology. He's mentioned that un minus p and vn minus p. If your sequence is mentioned like this, definitely it is a better than. That means if it is mentioned that un is a better than the vn only. So this is he mentioned only. So that means after using this one in 2004, Birinde, he developed this definition, and also he gave one important result also. I mean definition also, with using a very famous definition, that is I mentioned it in definition 1.2.1. Let A alpha and mentioned it AN. AN and BN are two sequences of real numbers. that converge to A and B respectively, and assumed that there is just a L is a limit enters to infinity modulus An minus A by Bn minus B is equal to L. This is published in fixed point theory and applications journal. Of course, later on it was name was renamed fixed point theory and algorithms from concept. Hindavi publishers. So in this, if you are observing this one L is equal to 0, then we say that the sequence alpha n converges faster than the sequence Bn to B. And second, if L, the value of L is lies between 0 to infinity, then we say that the sequence alpha n and Bn, sorry, An and Bn have the some rate of convergence. We can say that. We cannot assume that which one is the first. If L is equal to infinity, then we say that the sequence Bn is a convergence faster than the An also. Birinde actually he introduced this theorem. Introduced this definition. After that, he also introduced Birinde. Birinde XDB is a metric space taking an X is a self map on a X. Suppose that two fixed point iteration procedures UN and VN both converging to the same fixed points. UN is also converges to the fixed point, and VN is also converges to the fixed point. Both converges to the same fixed point of P. Then with the error estimates of D of UNP less than equal to AN, D of VNP less than equal to BN. And where AN and BN are two sequences of positive real numbers converges to 0. If AN converges faster than BN, then we say that the fixed point iteration procedure UN converges to B, then the fixed point iteration converges to procedure BN. And also similarly, and he proved it in the Jamfir-Scoop. He proved it, and also he proved it also in 1972. Jamfir-Scoop operators and proved that the sequence Picard iteration with an arbitrary initial point convergence to a fixed point such maps in the complete metric space. And Birinde compared, these are same paper also in the fixed point theory and application published paper, compared the rate of convergence Picard and Munn iteration procedure for Jamfir-Scoop operator and proved the following theorem. What he compared Picard and Munn iteration scheme with using of the Jamfir-Scoop operator. So after we can check it also. After replacing Jamfir-Scoop operator, we can apply any one of the also. You can also compare. How you can compare this one? See this one, especially and that theorem is mentioned. It is a very famous theorem. See this one. Let X be a Banach space and K be a self map on X and T is satisfied the Jamfir-Scoop condition. That is that they register real number ABC, and condition satisfies the first condition, second condition, third condition. That means Z1, Z2, Z3 mentioned it. For any initial value X0 and X and B a sequence of defined by Munn iteration scheme that is already mentioned in the previous. With the condition is 1, 2, and 3. One is take it the initial value is 1. Second is alpha and lies between semi-interval 0 to 1. Third is the alpha and his sequence is the diameters. Then converges Xn converges strongly to the fixed point of T. It is mentioned. It is proved in this one. Other than that, also moreover, the Picard iteration procedure with initial point X0 converges faster than the Munn iteration procedure. This is the new area, especially in the work in the fixed point theorems also. Fast iteration procedure. One question will be arise also, whether it is a Munn iteration only Birinde compared Picard and Munn. After that also we can observe that whether it is a Munn iteration scheme and Ishikawa iteration scheme, you can compare with using of the either B. Rhodes definition, otherwise Birinde definition. So many iterations already I posted in the previous page. We can compare which method scheme is adjusted. Then we can construct a table take it the one initial value using Picard iteration, how many iterations it happens for converging of the fixed point, first thing. Otherwise, one iteration you can follow, next Ishikawa iteration you can follow, and a CR iteration, SR iteration, whatever. You can find out the use of all iteration schemes. How many iterations are we are taken? Which method is taken very small low number of iterations? Convergent point, for reaching of the convergent point, which one is taken the very low number of iteration scheme? That is the best. So he compared. So for that purpose, if we studied this paper, definitely we can understand what is going to happen. So for this purpose, Birinde is introduced and also given one theorem in the what they mentioned, what is read it out in the previous mentioned it, this one. That is, he mentioned it one and Ishikawa iteration procedure, but it is a very difficulty procedure. And when we are given, then we has to take it out also. And now, in 2011, Sahu is also compared the rate of convergence Picard iteration process, Mann iteration procedure, and S iteration process to fixed point and proved that S iteration procedure converges faster than the fixed point iterations maps than Picard and Mann iteration procedure. And also now this is the question is given. Sahu is also compared. So actually, Sahu have a own procedure that is called S procedure, S iteration procedure, and he used which one is faster, and he proved it also. S iteration procedure is faster than the Mann and Picard only. Ishikawa they are not mentioned. My S iteration procedure is also faster, and also what he mentioned in the theme statement here, and let K be a non-empty closed convex subset of a Banach space. And K is self map on X, contractive map with the contraction condition K is 0 to 1, converges to P, Picard iteration T is the alpha and beta and B2 sequences lies between semi-interval 0 to 1, such that semi-interval 0 to 1, alpha n and beta n also, it is a typographical mistake, this is 0, and for n is equal to 1 to 3, and for some alpha beta is positive. If we taking here, it is a U1, V1, W1 is the same, lies between 0 to 1. Define the sequence alpha and beta and UN, VN, and WN and K as follows. VN plus 1 is called a S iteration is mentioned. It is already mentioned, but understanding purpose, I mentioned it again also. That is the two-step Mann iteration procedure is mentioned. Picard iteration is like this: VN plus 1 is equal to TXN. Mann iteration procedure is that is the xn plus 1 is equal to 1 minus beta and xn plus beta and txn also. And therefore, they mentioned it here it is, and rate of convergence is also mentioned. Un plus 1 minus p is equal to kn into 1 minus k into alpha into beta whole power n into un minus p. If you are applying the Picard iteration scheme, we are going to be B second condition, and if we are applying the C condition, we are going to be mentioned with the third condition. And also mentioned he proved it as iteration procedure is faster than the Picard iteration procedure, Mann iteration procedure also. And also in this area, I am also proved in the 2008, I think so, and also proved Mann iteration scheme is a faster than the Ishikawa iteration also, and myself and my research supervisor Babu and also, and more comparison for this works and comparison of convergence of iteration schemes. If you want to study, then refer, we can take it the my paper and Agarwal and Oregon and Sahu paper, Abbas paper, and Renucho paper, such and extra also. These are also works also there, this area also. In iteration schemes, in this area, we can change the scheme, and also second area is that we have to find out the rate of fastness of the convergence of the fixed point or not. Also, we are going to be checking that. That is also another area in the research, especially in this area. And so this one is that after that we are going to be talking in the stability. Where is the conditions? Higgs and cubic. Harder and cubic. 1 minute, please. Sorry for that. Stability area. Also, this is I would like to close this talk after discussion about the stability of fixed point iteration procedures also. So, stability area I am discussing this thing in present. I'm doing a research in this area, and especially in the application point of view in the chemical engineering area. That means we are applying these schemes, whether you are getting or not results, especially in the other boundary value problems also. But I am not touched in this. That topic is in this talk. That is the under developing that area. Therefore, I am not mentioned it. For that purpose, I would like to give a stability of a fixed point procedures also. So see this one. This is stability of fixed point iteration procedures. Time, rate of convergence, fastness, and next after that stability, we are going to be next show it also. I would like to close within 10 to 15 minutes. Let X be a metric space. T be a self map on X to X. Be a self maps on X. Ft is a non-empty. That means definitely fixed point should be there. And the general iteration procedure is defined as follows: that xn plus 1 is equal to f of t xn. F of t xn contains the parameters that define the iteration procedure. That is that one iteration procedure. Depend upon the procedure, we are going to mention whether it is a one iteration or Ishikawa iteration, Sawhooks iteration, or Renu-Chow's iteration, Abbas iteration, whatever. So f of txn, if we are taking the f of one iteration procedure, f of txn is equal to 1 minus alpha and xn plus alpha and txn. Suppose the iteration sequence xn converges to a fixed point of p and t. If the computation process due to various reasons, we may obtain sequence yn instead of the theoretical sequence xn. Especially in stability area, the fundamental thesis, Harder and Higgs, actually we are studying this area, established and systematical study of the stability of generally fixed point procedure in the setting of the metric spaces and the following. This is a very good book for those who are doing in stability, especially fixed point things. In that Harder and Hooke's point of view, in Harder and Higgs point of view, the definition of this one is that let X be a metric space and X is a self map on X, and we assume that iteration procedure is defined to the xn plus 1 is equal to f of t xn. Of course, it is correct. Suppose that the sequence xn is a converges to a fixed point of t, then we say that fixed point iteration procedure is a t stable. If the any arbitrary sequence yn in x limit n tends to infinity, epsilon error is converges to 0 if and only if limit yn is equal to p. Where what is the epsilon? Epsilon n is equal to d of yn plus 1 f of t yn plus 1. Difference between yn plus 1 and xn plus 1 difference for n is equal to 0, 1, 2, 3 up to so on. In the case of one iteration procedure, we say that the one iteration procedure is just stable in sense of the Harder and Higgs. And Harder and Higgs studied the stability of a Picard iteration procedure and contraction and the Jansen's co-operators also they mentioned. This is the is mentioned here. That is XDBA complete metric space and the T the self maps on X and Jansen's co-operator. TBA fixed point of T and X0 is the initial point and xn is a Picard iteration associated of t, and yn be a arbitrary sequence in x, and epsilon is equal to d of yn plus 1 ty for n is equal to 0, 1, 2, 3 up to so on. And then there is just a k. There is just a lambda belongs to 0 to 1 such that, and we can mention it. This is equation is mentioned here. D of P yn plus 1 less than or equal to D of P xn plus 1 and plus sigma 2 times of delta power n plus 1 minus k D of xk plus 1 plus up to so on like this. Limit enters into yn equal to P if and y equal to limit epsilon equal to 0. After that, Imbrue and Voltinovo is also, he used a plenty of contractor mappings and with using Aman and Ishikawa iterations also. He is also contributed very good, especially in this area. And in this area, he mentioned it is like this Voltinovo, and he mentioned it is used in these conditions. Let X be a metric space, let X be a metric space, K be a non-empty subset of X, and T is the self map on X, and T is said to be contract to like operator. He mentioned it is like this. He's used as a different type of. See this one. And this is the 1.3.3.1. That is the D of txt when less than equal to delta times the D of xy plus phi of D of xtx for all xy and x. Here we note that every contraction mapping is a contract to like operator. Definitely phi of, if phi is an absent, definitely it is a contraction condition, lambda is 0 to 1, where a contraction condition. That a contract to like operator is not a contract to condition. This example is also mentioned in that paper also. Further, a contract to like operator may not have a fixed point. We discussed in especially in further talks also, and he also mentioned in a Berinde's iterative procedure scheme also. And this is the contract to like operators continues at its fixed point, and Nimru and Voltenwo let actually be a complete metric space, and he proved it this theorem, and T be a contract to like operator. Suppose T has a fixed point, then the Picard iteration procedure is a T stable, and also he proved it another theorem also with using of the Mann iteration scheme. Same mentioned, it is mentioned in a normal linear space. They mentioned T the self map on X to X is a contract to like operator. Suppose T has a fixed point of P for any initial value x naught in X, that x naught be sequence defined by a Mann iteration procedure 1.1.2.1 with the especially alpha and lies between the 0 to 1, and also initial value should be more than non-negative, and positive also plus positive value. Then Mann iteration scheme procedure is a T stable. And also this is the more literature, we can take it the Vasilike paper and Chidumi paper also, that is not mentioned here, and Rhodes papers also. Sorry for the inconvenience. Sorry for the inconvenience. And two mentioned here, it is Ernivo that the operator has the limit force. Property of the Picard iteration procedure. This is the D of yn plus 1, yn, Tyn is converges to 0. And last one, I would like to show another iteration process, stability procedure definition. This is the Russ definition. Picard iteration procedure is the T step is stable with respect to the operator T. One is the it is convergent with respect to T, and T has a limit shadowing property with respect to the Picard iteration procedure. And he's also used another area, perturbations. Perturbations is also mentioned it here, but I'm not working in this area. Dr. Professor D.R. Sahi is very developed this area in perturbations area with using of the S iteration schemes also. So this is the definition. And last definition, last two definition I would like to show 1.3.10. This is called admissible perturbations area. So I would like to stop now. I would like to pause give a talk to the question area. Sir, with your
Dear participants, those who are having doubts, please ask your questions one by one. Sir will clarify the doubts. Dear participants, those who are having some doubts, you can ask. Sir is available actually. He can clarify your doubts.
Dr.
Or
Varaprasad,
raise your hand.
Sir, namaste,
Or
sir.
post your question in the Q&A box.
Sir, thank you very much, sir, for your excellent lecture on innovative methods using contractive mappings.
Sir, thank you very much.
Your presentation on the convergence rates and stability is highly informative, sir, and really appreciated.
Thank you very much, sir. Thank you very much. Actually, this area I'm applying in the, especially in the application point of view, on the boundary value problems in the chemical engineering side, with using of the Green's function.
Karunakar, sir, please once again call our participants, sir. Karunakar, sir, please announce once again, sir.
Sir, those who are having doubts, please, you can post the question in your Q&A box or ask the question directly. Sir can clarify your doubts. Dear participants, those who are having doubts, you can post the question in Q&A box or you can ask the question directly. Sir will clarify your doubt. Any participant? Sir, there are no questions. Actually, they are not asking any questions, sir.
Before going to the conclusion, I would like to give a small message to the dear participants. Dear participants, if you have any queries, if you want to ask in this regard of iteration procedure, my mobile number is also mentioned in the, I think so, in the brochure also. You can call anytime, and also you can find out my email address as with my research papers. You can pose your questions through email address, otherwise a phone call in the any time, except in the sleeping time. Other than that, if you are mentioned any time, especially in this area, definitely I will try to give your answers also affirmatively. And also I'm doing present research in this area. I'm also in different mode. Different mode means in the sense of, especially in the applications. I'm trying in the chemical engineering, mechanical engineering, and boundary value problems. So how we are going to apply the schemes in the, especially in the boundary value problems with using of the what is the Green's functions. If you are using the green functions, otherwise the fractional derivatives also I'm trying to apply. Recently, 1 or 2 papers also published. I am also contributed a small applications in the fractional calculus area also. So anybody, I'm given in this talk only primary information, what is available in the mathematics literature, especially in the specific field. Right now, in fixed point theory, this is the very emerging field in doing research. If anybody wants to do research, these are, I think so. These information is a prerequisites. Only I am giving abstracts only. If anybody really interested to do this work, definitely ask me. I will provide some information. Maybe it may be useful to you for further research also. At your time, if you have any doubts, definitely I will clarify at that time also. If you are not able to pose your questions in this platform, please take it to my number. You can ask in this area, definitely I will try to solve your questionnaire to give an affirmative answer. I will give affirmative answers also. So this is, I would like to convey this information to the respective our participants. Thank you very much. And I would like to go more for the sir. Please, sir, please.
Okay, sir.
Sir,
Please wait.
Karnataka, sir, we can conclude the program, sir.
Okay, sir. Thank you, sir, for your lecture.
Thank you. very
Iterative
much.
procedures for approximating fixed point of contract to type mappings. Thank you, one and all, for your good response and valuable support. Expecting the same cooperation for the remaining sessions also. Today's session concludes with a vote of thanks by co-convener Dr. T. Srinivasrao Garu.
So good evening to all. On behalf of the Department of Mathematics and the participants, I would like to express my heartfelt thanks to our today's resource person, Dr. KNVV Varaprasad Garu, who gave such a good and information on iterative procedures for approximating fixed points of contract to type mappings. In this talk, Dr. KNVV Varaprasad Garu have discussed various iterative methods using contract to mappings, focused on their convergence rates and stability. Also examined how some methods converge faster than other methods with the support of analytical findings and numerical examples. It is a very active area of research going on now. Despite his busy work schedule in the university, he cordially accepted our invitation immediately and gave a talk in today's session. Thank you very much, sir, for giving such a wonderful presentation. Today's session has been enriching with Dr. KNVV Varaprasad Garu presentation on applications of fixed point theorems, which has inspired new ideas among the faculty members and helped to strengthen their research skills. Thank you, one and all. So within a few minutes, feedback link will be shared in both the WhatsApp groups and YouTube channel. So please fill it and submit before 8 p.m. today. Thank you.
Thank you very much for giving this opportunity to the entire team
Thank
of
you, sir.
the Department of Mathematics and Biomedical Engineering College. Thank you very much, sir. Thank you.
Thank you, sir.
Thank you. Shall I leave, sir?
Thank you,
Yes, sir.
Prasad Garu.
Thank you, sir.
Thank you very much, sir. Thank you. We'll contact you in the separate. Thank you.
Thank you, sir.
Thank you. Thank you very much.